This lecture is all about presenting our data into the graphical form. So we're going to look at how to draw the bar charts, pie charts, parental diagrams, or cumulative percent polygon. Now with a bar chart, as we know, it's bars that shows categories, or the length of which represents the amount, frequency, or percent of values falling into a category. The one that is being shown to you, it's a horizontal bar chart. So a set of disjointed bars of equal width drawn such that each bar represents one category of a variable and its height is proportional to the frequency it represents. That is now when it's standing up vertically. Now a pie chart is a circle that has segments, that we may say slices, that presents categories, and each of these segments of the pie chart varies according to the percentage of each category. So a pie chart is a circle drawn to depict a variable that the circle is divided into segments, each of which represents one category of the variable, and the size of the segment is proportional to the frequency of the category the segment represents. So to get these segments, which is proportional to the category it represents, this is where we take the frequency of the class divided by the total frequency of the variable times 360, the circumference of a circle, to give us the size of the segment. Now if we take the following example to get the segments of a pie chart, we have this working table. The distribution of UNAM academic staff by nationality. If we have Australian, Chinese, Tanzanian, South African, Zambian, and Malawians, then the frequency given there relating to each nationality. So the size of the segment in degrees is then given the frequency of the segment over the total frequency to give us the size of the segment. So in this sense, we now can say for Australia, we take 5 over 70 times 360, giving us 25.7. That is now the degrees that you're going to use in your construction of your circle to get this segment. So in this case, you need to make use of a protractor and a compass to draw your circle and the segments. So if you add up the total segments, they're supposed to give you 360, but due to rounding of error, it's always going to give you something that is close to 360 or off by a margin of decimals. Now the pie chart can be used to compare things together. So the two charts, when you're comparing the pie charts, should be drawn on the same page or next to each other. And then the next thing is that the size of the two circles should not be the same, since the sizes of the two populations are not the same. So this brings us to the point where we take the radius of the smaller population, denoted with a small letter r, and then this capital letter R represents the population with the biggest observations. And then in this case, we also have the totals for the respectful samples or populations. So we make use of the formula r squared equals to t squared over t squared. So in this case, one of the radius should be given to you to make use of the formula. So whichever radius is given, you make the other one the subject of the formula to obtain what you need. The totals can be computed from the data set that you have. Now, the Pareto diagram is used mostly to organize categorical data. It's used to display data that are measured on the nominal scale. So this one looks like a bar chart, a vertical bar chart. The only difference is the categories are shown in a descending order of frequency. And then on top of this, a cumulative polygon is shown in the same graph, where you start adding the frequencies from the first one to the next and giving you an upward sloping line. So we use this to separate the vital few from the trivial many, and it looks like this. As we have said, it's the same as a bar graph, but the bars are in ascending order from the highest to the lowest, and then the frequencies we take from the first bar, adding it up to the last one. That gives us now the Pareto diagram. Now this is just a summary of the charts for numerical data. For numerical data, we have the ordered array and the frequency distributions and the cumulative distributions. The ordered array is the stem and leaf display, whereby the frequency distribution and the cumulative distribution is the histogram, polygon, and the ogive. Now the ordered array is a sequence of data in rank order from the smallest value to the largest value. It shows the range minimum value to the maximum value, and it helps to identify outliers as well. So if you have a survey of college students, the day students and the night students, you now arrange that data that is given to you in an array from the smallest to the largest. Once you have done that, then we can proceed. This data is already arranged for you. Now, this data we can make use of it to draw a simple way to see how the data are distributed and where concentration of data exists. We separate the sorted data series into leading digits. The leading digits is what we call the stem, and the trailing digits is what we'll call the leaves. In this data set, the leading digit will be 1, 2, 3, and 4. The first digit of each number, whereby the trailing digit, the leaves, are going to be the second digit. Okay? So here we are saying a stem and leaf display organizes data into groups called stems, so that the values within each group, the leaves, branch out to the right of each row. Now, for the day students, we have the following stem and leaf display. So the stem where it has 1 and the leaf that has 6, 77, 888, 99. It reads as, where you see the 1, if you come to this leaf, the stem is a 1, the leaf has different numbers. So if we look at the leaf, we see the 6, but the stem is a 1, so that is 16, 17, 17, 18, 18, 18, 19, 19. So that is how it goes. So you can now have these as your stem. Now, organizing the numerical data, the histogram. A vertical bar chart of the data in a frequency distribution is called a histogram. Now, a histogram, compared to a bar graph, has no gaps between the adjacent bars. And the class boundaries or class midpoints are shown on the horizontal axis. Now, the vertical axis is either frequencies, relative frequencies, or percentage. The height of the bars represents the frequency, relative frequency, or the percentage. The most important thing here is that the x-axis shows the class boundaries or the class midpoints, not the class limits. Now, using the example earlier that was used to construct the constituency table, bringing it here, we can now make use of it to draw the histogram, and it gives us a display as the one that you are seeing. On the vertical axis, the y-axis, that is where we have the frequency. And take note, where the frequency is, give it the appropriate name that the data is representing, as well as the x-axis, give it the appropriate name that the data is representing. But in the terms of construction, the x-axis shows the class boundaries or the midpoints. So in doing that, you first need to get your class boundaries, and then you draw your class boundaries against the frequency to get your histogram. This is just the difference between the bar chart and a histogram, whereby the bar chart is detached, the histogram is jointed. The bar chart had equal widths, the histogram bars width vary according to the data. There's spaces between the bars are equal for the bar chart, and there's no spaces between the bars for the histogram, and the bar height are proportional to the frequency the bar represents for the bar chart, and for the histogram the bar area is proportional to the frequency the bar represents. Now, the histogram is ideal for both qualitative and quantitative data, whereby the histogram is only ideal for quantitative data. Now, the polygon itself, we can say a percentage polygon, which is formed by having the midpoints of each class represents the data in the class, and then connecting the sequence of midpoints at their respectful class percentages. The cumulative percentage polygon, or ogive, displays the variable of interest along the x-axis and the cumulative percentage along the y-axis. This is useful when there are two or more groups to compare. So, the frequency polygon literally is the midpoints of your histogram. It's drawn on the same part as your histogram. When you take your histogram and you mark out the midpoints and you joint them, it should give you the frequency polygon. It also make uses of the midpoints on the x-axis and the frequency on the y-axis. Now, the ogive is drawn to represent cumulative frequencies, and there's two of such. One represents the cumulative frequency less than a certain reference point, and the other represents the cumulative frequency more than more than that point. So the former in this case is called the less than ogive, and the latter is called the more than ogive. Using this data, the working table for construction of ogive for the age distribution of students. You have your age grouping, whereby you have the first three groups with a width of 5, and the last two should be with a width of 10. If you take note, when we're doing the frequency distribution, that in cases where you do not have the same age group class intervals, that is when the last ones has fewer data, whereby you now need to group it, or the data is just a lot for it to be falling in one group. So hence that is why the last two groups in this case are bigger than the others in terms of the class width. So we have this. Let's get back to the ogive. With the ogive, we need to have our classes closed. So how we close the first class? This is also the same for histograms when you need to construct a histogram. The first class is closed with respect to the next class, the second class. That means the first and the second class should have the same class width, and the last one and the second last one should have the same class width. Okay. Now the lower class boundary for the first one will be 14.5, and then the next one will be 19.5, 24.5, 29.5, 39.5, and 49.5. So these are the lower class boundaries that you're going to use in the construction of your ogive. Now the cumulative frequency with a less than, we always, take note, always starts off with 0 for the first interval. It's 0. And then we take the frequency of the first one for the next, so that one is going to be now 5. Now we have 0 plus 5, then 5 plus 140 gives us 145, and then 145 plus 129 gives us 274. That plus 48 gives us 222, and 322 plus 22 gives us now 344. That is now the same as the total. As you can see, each of the less than cumulative frequency corresponds to a given lower class boundary. Okay. Now the more than, we always start off with a total frequency and we subtract. So that means 344 minus 5 gives us 339. Minus 140 gives us 199. 199 minus 129 gives us 70. 70 minus 48 gives us 22. 22 minus 22 gives us 0. So for the more than, you'll always end up with 0. And on the lower class boundary, take note that the 49.5 is closing off your class intervals. That is now the upper one, which is basically the upper end of the last interval, which is the beginning of the next one. That is hence whereby we have the total, we have 49.5 as the lower class boundary. So now once you have obtained your less than and more than cumulative frequency, you now construct your ogive, and it looks something like this. Now once you have constructed your ogive using your less than lower class boundaries, and it looks like this. The blue line is the less than ogive, the red line is the more than ogive, and you can answer respectful questions that are of interest using the ogive. Now with the ogive, you can also construct the cumulative percent polygon. That one deals with the lower class boundaries. If you're now doing this, you draw in an ogive, the percentage of the observation less than each of the lower class boundary are plotted versus the lower boundaries. So in this case, you can be asked to strictly draw the less than ogive, and then you'll only have this, what is being displayed. If you are asked to draw the more than, then it will start from the top going all the way down. Now for cross tabulations or cross tabs is used to study patterns that may exist between two or more categorical variables, and this cross tabulation can be presented in tabular form, that is constituency tables. Graphical form is side-by-side charts. Now a cross classification or constituency table presents the results of two categorical variables. The joint responses are classified so that the categories of one variable are located in the rows and the categories of the other variable are located in the columns. The cell in the intersection of the row and column are the values in the cell representing the data corresponding to the specific pair of row and column categories. A useful way to visually display the results of cross classification data is by constructing a side-by-side bar chart. Now with the constituency table, this one will deal with it more when we do probabilities and then when we also do index numbers. This is just an illustration of how a cross tabulation looks like, where you have the importance of brand name, and then where you have gender, which is male and female, and you get the respectful values and the totals, and then you can make use of this to answer questions. Now a side-by-side bar chart is what we have here. Now a scatter plot are used for numerical data consisting of paired observations taken from two numerical values. One variable is measured on the vertical axis and the other one is measured on the horizontal axis. Scatter plots are used to examine possible relationships between two numerical variables. So the scatter plots actually tells us the relationship that exists between two variables. If you plot your scatter plot and it's upward sloping, then that one you can say it's a positive relationship, and if it's downward sloping, it's usually a negative relationship. With scatter plots, we'll come to this aspect again when we do correlation and regression later on. Now, if you take volume per day and cost per day as an illustration to draw a scatter plot, so you draw each values against each other and you do not join the dots. The dots are left unjointed for a scatter plot. Now for time series, a graph displaying changes in a variable at different points in time. It shows time measured in units such as years or months, days, etc. on the horizontal axis, and the frequency, percentage or rates of another variable on the vertical axis. A time series plot is used to study patterns in the values of a numeric variable over time. Now with a time series plot, the numeric variable is measured on the vertical axis and the time period is measured on the horizontal axis. Now if we take the number of franchises as an example in the years, if we plot them, it gives us a scatter plot as such, but for a time series, the points are jointed together, so that in this one where you have this, you join the points together so that you can see the trend that exists. Now this brings us to principles of excellent graphs. The graph should not distort the data. The graph should not contain unnecessary ornaments, sometimes referred to as junk. So the scale of the vertical axis should begin at 0 at all times. You begin with 0 and you put a break in the line if your next number is a higher number that gives you a huge quantity, a huge values. So you put the break and then you start off counting with the usual. Or otherwise your graph will be drawn way off the page or way off on one side. And then all axes should be properly labeled, and the graph should contain a title, and the simplest possible graph should be used for a given set of data. So why we use charts and graphs? What do we choose? What do we lose? The ability to examine numeric detail offered by a table, potentially the ability to see additional relationships within the data, potentially time. Often we get caught up in selecting colors and formatting charts when a simply formatting table is sufficient. And what do you gain? The ability to direct readers' attentions to one aspect of the evidence, the ability to reach readers who might otherwise be intimidated by the same data in a tabular format. Then the ability to focus on bigger picture rather than perhaps minor technical details. Now this is just a summary of the graphical procedures. We have our data. Once again, we have the qualitative and quantitative data. Quantitative data is presented by tabular methods and graphical methods. And quantitative data is also presented by tabular and graphical methods, and each method is being shown below. For tabular methods, it's frequency distribution together with its relative frequency and relative percentage, and also the cross tabulation. Graphical methods for qualitative is the bar chart and the pie chart, whereby for quantitative data, the tabular methods is the frequency distribution, relative frequency, percent frequency distribution, cumulative frequency, and cumulative relative frequency distribution, and cumulative percent frequency distribution, and cross tabulation as well. And the graphical methods for quantitative is the dot plot, histogram, ogive, stem and leaf, and scatter plot. That now brings us to the end of our presentation.